In this video, we continue to look at the proof of the first isomorphism theorem for rings. And the first isomorphism theorem says, if phi is a ring homomorphism from R to S, and I is the kernel of phi, then the quotient ring R mod I is isomorphic to the image of phi. In the previous video, we started the proof by defining a map pi from R mod I to phi of R as pi of R plus I was just phi of R for every single left coset R plus I inside the ring R mod I. And in the previous video, we showed that this map pi was well defined. In other words, we showed that if R1 plus I and R2 plus I were exactly the same coset, then pi sent R1 plus I and R2 plus I to the same place. And as part of that proof, it turns out that if R1 plus I and R2 plus I are the same thing, then phi sends those two coset representatives to the same place. In this video, we turn our attention to showing that pi So we're now going to show that pi, which goes from R mod I into phi of R, is a ring homomorphism. In other words, we need to show that pi preserves the ring operations of addition and multiplication. So we will first show pi preserves ring addition. So let's look at this. Let's let A plus I and B plus I be any two elements of our quotient ring R mod I. Then we have the following set of calculations. Pi of A plus I plus pi of B plus I will be equal to phi of A plus phi of B by the definition of pi, the map from R mod I into phi of R. But phi itself is a ring homomorphism, and so that I know that phi of A plus phi of B is phi of A plus B, and I know this since phi takes R into S, is a ring homomorphism. But the definition of pi says that phi of A plus B is just pi of A plus B plus I. So that again is the definition of our map pi. And then I know that this particular left coset can be rewritten as A plus I plus B plus I. And so I know that pi of A plus B plus I is just pi of A plus I plus B plus I, and this is by the definition of the addition inside the ring R mod I. And when we look at this, what we see is that pi does indeed preserve addition. So this particular thing has been done. Okay, what we're now going to do is move on to showing that pi preserves multiplication. So pi preserves multiplication. Again, we're going to let A plus I and B plus I be any two elements of R mod I. And look at this set of calculations. Pi of A plus I times pi of B plus I is going to be phi of A times phi of b, and this is by the definition of pi, our map from R mod I into phi of R, which is a subset of the ring S. And phi itself is a ring homomorphism, and as a consequence, phi of A times phi of B is just phi of AB, and this is, since phi takes R into S, is a ring homomorphism. But we can now use the definition of pi again, and phi of AB is just pi of AB plus I, and that's again by the definition of our map pi, which takes R mod I into the image of phi. And coset multiplication is well defined in R mod I, so this coset can be rewritten as A plus I times B plus I, and hence pi of that coset can be rewritten as pi of A plus I times B plus I, and I know this by the definition of times inside the ring R mod I. And so we have that pi preserves multiplication, and that lets me say that I know that pi is a ring homomorphism from R mod I to phi of R. Well, at this point, the question is whether or not phi is a ring isomorphism. We will look at that in the next video.